Hi, and welcome back to my Physics Online video lecture series. Today's video we're going to be talking about electric potentials in the context of equipotential surfaces and electric field lines. So what are equipotentials? What does that mean? Break the word apart, it basically means equal potential. So it's essentially depending on what you're doing, lines, curves, or surfaces within a region of space, or even entire objects, over which the potential does not drop from one point to another as long as you stay on or are moving from one point to another on the equipotential. So what do they actually look like? Well, you could have a series of charges aligned in such a way that if you were to put two probe lines anywhere on this black line, so you have a voltmeter, you attach one lead, say here, and another lead here, then the voltmeter reads 0. And likewise, if you were to put one lead, say, right here and another lead, say right here, this would be delta V0. So this right here, delta V equals 0. This right here, delta V equals 0. But if we were to attach a lead, say from this point to this point, this one, delta V, does not equal 0. So we basically end up having a voltage drop from one of these lines or curves to another. And kind of the analogy that you could use is that these equipotential surfaces, or at least when you're on a two-dimensional map, these become equipotential lines or equipotential curves. These are kind of the equivalent for electrostatics. So we'll write electrostatic here as let's say a topographic map, whatever you want to call it, is to gravity. And in fact, a topographic map is a gravitational equipotential energy map, because U is equal to mgh if you're dealing with gravity. So equal height lines, equal elevation, is equal to equal energy. So what do these look like then, or how do you get them? Well, we have kind of danced around this idea a little bit. Essentially, the electric field is the gradient. So essentially what that means is that E is equal to delta V over delta X to get E sub X. Or put differently, electric field is the gradient, or if you'd like to think of it, it's the slope, but in 3D, of potential. So this right here is E sub X, E sub Y would be negative delta V over delta Y, and E sub Z is negative delta V over delta Z. These are all actually average field strengths. As long as you have a uniform electric field, then the average will be equal to the value of the field anywhere in space. So practically speaking, what that means is that the electric field will be E will be perpendicular to equipotentials. And always points from higher potential to lower potential. All right. So coming back to this idea of having a charge distribution, let's say that we have our plane of positive charges like this, and maybe we do this for a pair of planes of charge. So maybe over here I have now some negative charges. We actually know what the electric field looks like for this because we've drawn it before. We expect the field lines to basically just run from one plate to the other, or one plane to the other, perpendicular to the two planes. And essentially, if I've oriented these two planes in this view vertically, then the field lines will basically be horizontal. So what I've drawn here now is the electric field between these two plates, and outside the two plates it actually should be zero. So the equipotential lines basically should just be perpendicular to these field lines. And so this right here would be one line. I would get another line maybe right here, and so on. And they would basically just all be equally spaced, oriented perpendicular to the field lines everywhere. And essentially I could go through and sort of like label the values that these would have. One way of looking at it is that as I move a voltmeter probe around to map them, maybe I happen to put my common right here, and so maybe I really should do these in red just to match what the voltmeter would be doing. Usually you use the black probe on the voltmeter to be kind of common, and then the red probe is to your source relative to that common or to ground. So these right here would be where I'm putting my red probe line, and then over here is where I'd be putting my black probe line. So I'd essentially have like one probe right here, and then my red probe would just be going to different of these equipotential lines and measuring. And so what you could do in principle is you could move the red probe up and down the field line, and you'll just get the same voltage reading everywhere on this equipotential line. And so maybe if this happens to be a 2-volt line, this would be 4, 6, 8, 10, 12, 14, 16, and then over here would be 18 if you were to go along on this plate anywhere. And this would be the 0 volts relative to ground. Now notice that the E field are pointing from the high 18 to the low 0. The other thing is, for what it's worth, we could actually determine the E field strength here. Since the field is oriented entirely along X, we could do something like E is equal to E sub x is equal to delta V over delta x. And so we could measure the distance between one of these and the next. The distance on my screen seems to be of order 1 centimeter between each set of lines. And so how many lines are there? We got 1, 2, 3, 4, 5, 6, 7, 8, 9 centimeters. So this would be 18 volts divided by 0.09 meters. Okay. So 18 over 9 would have been 2. So this is 200. So my electric field strength here is 200 volts per meter everywhere. And notice that the unit here is now volts per meter. This is the same equivalent unit to newtons per coulomb. So another way of putting the voltage, another way of putting the electric field strength is in terms of the units of volts per meter. That also means, for what it's worth, that the electric field flux is now volt times meters. For other distributions, you can kind of sketch the fields, but you can't really you can sketch the fields and you can use the field sketch to sketch the equipotential lines. But without using calculus, you can't really compute the values very well. You might be able to compute them otherwise, like we've kind of given what the result is for a coulombic potential. And so if you have a point charge right here, and therefore you have field lines that are like so, where they just kind of point out from that charge, then you end up expecting to get equipotential surfaces that are everywhere perpendicular to these lines. And so in 2D, the equipotential curves must be everywhere perpendicular to these radial lines. Well, that is just the same thing as having a set of concentric circles centered on this plus. The difference is that because the fields are getting farther apart, or the field lines are farther apart as you go farther away from the charge, these will not all have the same spacing as they did on the previous configuration. So I've drawn here a set of equipotential curves for this point charge, basically a 20 volt, a 10 volt, and a 5 volt curve. And the radii of these curves are such that the radius to 10 is twice the radius to 20, and the radius to 5 is twice the radius to 10, which incidentally means 4 times the radius to 20. So essentially you've got these concentric circles. They're all centered here on your positive charge, but they're all getting basically larger circles as your equipotential value is getting smaller. And so, and these are kind of like relative to infinitely far away. So if I had my other probe at ground or at infinitely far away from my common probe and my red one was here, I'd get 5 volts here, 10 volts here, 20 volts here. If I wanted 40 volts, I'd have to go half again the distance from this one to the center of the point charge. This charge could represent a spherical distribution or a point charge. It's just if it's a spherical distribution, then the circles kind of stop at the surface. But in any case, that is kind of a simple sketch of or explanation of how to draw these equipotential surfaces. What they're doing is telling you surfaces, or in 2D curves, lines, whatever, along which it doesn't take any work to move a charged particle from one point to another. So if I wanted to move a charged particle from this location to this location, that takes 0 total. And that's true for any pair of arbitrary locations that are on a pair of curve. So A to B, C to D. Basically, any point on this outer circle to any other point on this outer circle to move a charge from one point to the other will require no work. Likewise, any point on this middle circle to any other point on the middle circle takes no work to move a charge from one to the other. And it takes no work to move a charge from any point on this innermost circle to any other point on the inmost circle. Conversely, if I wanted to move a charge from, let's say, the inner circle to one of the others, so like from point, let's say, F to C, you would require a work of Q times delta V, delta V being 20 volts minus 10 volts. Or I should say properly, like, you're actually not having to do work because the system will do work for you. So you could write it as 10 volts, the final, minus 20 volts, the initial, which is essentially negative of Q times 10 volts of work. So you don't have to do work, the system will do work for you. But if you wanted to go from C to F, you would have to put in 10 volts times the amount of charge that you're moving from C to F. And likewise, if you wanted to go from A to C, you'd have to put in 5 volts times the amount of charge that you're moving from A to C. Okay, so that's basically how these equipotential surfaces work. No pun intended. That is what they do and what they tell you, and that is how to go about drawing them or figuring out where they should go for a given charge distribution. So hopefully this video has helped you to understand this topic a little bit better, and thanks for watching.